Welcome back to part 3 of the Prospect Course 209 for the Geotechnical engineering portion. We're going to talk about developing performance functions. Some things we're going to talk about are poor performance versus levee failure, geotechnical failure modes, performance function development and approaches, applying these approaches to failure modes, and combining individual failure mode probability curves. So we'll jump right into it. So typically for levees and embankments, dams and levees, there's several common failure modes, including embankment instability, under seepage, through seepage, wind or current induced erosion. And these failure modes can be exacerbated by other factors such as encroachments, utilities, animal burrows, poor vegetation on the levees. So those can contribute to the likelihood of or resiliency of a structure. Here's an example of several failure modes that were identified for a specific project. There was slope instability of the landside levee slope, and so in this failure mode, water seeps through the levee, causing a reduction of effective stress of the levee soils, and the land side of the levee fails, leading to loss of crest elevation, water overtopping, and levee breach. I think what's important to take away from this slide is that an understanding of how the failure mode goes from loading to failure is important. In some of the previous guidance, it has been somewhat unclear about understanding levee poor performance versus failure. And so I think the new engineering technical letter 588 tries to make the important point that the system response curve represents the conditional probability of failure leading to inundation and associated economic or life safety consequences. So what that means is the levee fails and something gets wet. Okay, a person, building and its contents, or something happens. So that's different from poor performance, where you might have levee damage, but that doesn't necessarily lead to breach. So I think that's the important distinction here. So we're going to go through and talk about that a little bit more in the next couple slides. Here we have an event tree for a full event progression. And so you have the hydraulic loading on the left side. There's a defect in the levee. Then the levee either has a factor safety less than 1 or greater than 1. And it's sustained long enough to progress, and then the levee fails and consequences or impacts are realized. So these are kind of the basic structure of how event works. These intermediate nodes, like node 3 and node 4, would be where the most heavy engineering analysis is needed to estimate probabilities that certain factors of safety are less than 1 and these kind of things. Node 2 is really where you would say maybe there's a certain condition that exists, a blanket problem or a sand layer that we don't know about. And so here, where the probabilities of these kind of uncertainties might be, like, are we certain we have a seepage cutoff or not certain? And if it turns out to be important, like if through sensitivity analysis that this matters, field borings and other investigations might be needed to answer whether or not the defect occurs or doesn't occur. So here's some examples of the poor performance versus levee failure. Here we have a picture of a levee breaching. This is levee failure. So the water's loaded on the left, breach happens, and something gets wet on the right. Here we have just poor performance. So this is not levee failure. The levee experienced a lot of damage due to some load, but if you can see the water's on the left, it's still dry on the right. So this would count as poor performance and not levee failure. This might be important for estimating maintenance and life cycle costs, but not necessarily for the inundation AEP kind of calculations. Here we have a levee being loaded from right to left, and this is the Sutter bypass levee in 1997, and we have a levee failure. Similar to the second photo we looked at, we have a slope failure, but not a levee failure, and so this would be considered poor levee performance in this slide. When we're developing geotechnical system response curves, there are several methods that can be used, and sometimes they're used sort of combined. And so these are kind of discussed in ETL 588. And so probably the most simple one is like the empirical methods here. And so that is where we don't know much details about our project, or we don't do much analysis, and we just estimate the failure probabilities based on its past performance or performance of similar projects that have similar characteristics as the one we're looking at. Also, expert elicitation is somewhat simple, except you have a group of experts, you postulate failure modes, and the experts kind of agree based on judgment and experience on probabilities of the different nodes in the event tree. And in the frequency-based and probabilistic limit state, these kind of go together, but the frequency-based is you use a full event tree. There's probabilities assigned at each node. You know, for some nodes you might use judgment, and in some you might use detailed calculations, and the probabilistic limit state calculations might be used in some individual nodes in a frequency-based analysis. Here's like an example of a calculation that might be used in the intermediate node, where you want to know if the failure mode, which is a seepage and piping failure mode, is likely to occur. So what we have here are, given this load, H equals 20, we have some Q variables, the permeability ratios of the K blanket and the foundation sand, that's in this first column, the thickness of the clay layer, the thickness of the sand layer, and we vary those plus and minus from the mean, and we run our calculations, and we calculate if we have a factor of safety less than 1. And so this would be an intermediate node, and so in this case we have a, I think it's covered up by my window, but we have an 87% chance that the factor of safety is less than 1. This doesn't necessarily mean that the levee fails. First, there might be some other nodes that the water has to come to 20, so there's a certain probability of that. Then there might be an intermediate node that the water is there long enough to initiate the seepage failure mode, so there might be some chance that the water is only there for a short duration and isn't there long enough. And then finally, the erosion has to cause piping, but the piping has to progress long enough such that it collapses a levee. So that might take some time after the factor of safety less than 1 is realized for the levee actually to fail. So that kind of illustrates how you know, some heavy calculations are just part of the full picture of how the levee might fail. And this talks about how we want to represent the failure of the system, not just, and so we might not know where the critical point of a system levee might fail, and there might be several locations of interest. And what we can do is we can evaluate the potential failure modes at each of these locations, location 1, 2, 3, and then pick the highest failure location, and we use that as representing the overall chance of overtopping. So in this case, location 2 has the highest chance of overtopping compared to location 1 and location 3. So that would be, that failure mode would most likely occur at location 2. Under seepage would most likely occur at location 1, and so forth. And so we pick where the different failure modes are most likely to occur, and then we plot them with the probability of failure and the annual exceedance probability, and we combine them like this, where the overall probability of failure equals 1 minus the product of 1 minus the probability of failure of each failure mode. So here we have all the different failure modes at the different locations, and we combine them, and we use this to represent the overall probability of failure of that system. So different locations contribute partly to the overall failure mode probability, the overall probability of failure. All right. So with that, I think just to remind what we learned the difference between pore performance and levee failure. We learned about common geotechnical failure modes, and we discussed how there might be different approaches to develop performance functions, and how we might combine individual failure modes to a single performance curve to represent the performance of a specific levee system.